Okay. Can you all see my screen?
Yes,
Okay. So once again, I'm happy to be on the same stage with different reputable speakers. And this afternoon, in UK, this afternoon here in UK, I'll be
please click
speaking.
on slideshow.
Okay, hold on. Um, okay, is it
It
okay now?
started now.
All right. Okay, so it's the afternoon in UK, and I'll be speaking on this topic: enhancing stability in machine learning explanations with S-Line. And so this is the overview of everything I'll be talking about. I'll be giving a brief description of the topic and the objectives and a few analyses I conducted on the topic and the conclusion. Talking about the topic, enhancing stability in machine learning explanations with S-Lime. The first thing I'll be talking about is why machine learning explanations to start with. And so much has been talked about different machine learning algorithms that have been used to make predictions in different industries. As of now, there are several advanced machine learning algorithms that exist: neural network, gradient boosting, regression models, and these models have been found to be accurate. They've been found to make accurate predictions. But then there is a trade-off between the accuracy of advanced machine learning algorithms and the explainability or transparency of these models. When we look back at simpler models like linear models, even though it's easy to understand how they make their predictions, it's easy to identify the variables that they use to make predictions, but then it's though it's more explainable, they are simpler models, but then they are not really accurate when it comes to fitting into much more complex data sets that we have these days. But then when we apply advanced machine learning algorithms that captures more complexity of the modern data that we have in this era, but then it also sacrifices transparency. And this is an issue in safety critical industries like the aviation industry, also in the medical industry, because it's difficult to implement certain models that stakeholders, especially non-technical stakeholders, find opaque or find non-transparent. And this is the reason why we call such kind of model black box. We call them black box because even though we can easily like identify with the accuracy in the output that it generates after carrying out predictions, it's difficult to understand which variables is being used to make the predictions. So, and this is the problem with the black box models. First is difficulty in validating model decisions. So it's difficult for non-technical stakeholders to understand or to really to understand if there's any bias in the decision that is being made by this model. And this is an issue also in the finance industry where, for instance, models maybe are used to predict the credit worthiness of their customers. But then depending on how this model is being trained, sometimes there might be bias based on variables like race, variables like age, for instance, and this is sort of an issue for non-technical stakeholders, the non-transparency, and that is the essence of explaining black box models. That's the essence of that is the reason why a lot of research is going into different research methodologies or different methods that can be used to really make black model transparent, make non-technical stakeholders have much more confidence in implementing these models in safety critical industries. So the essence of explaining black models includes the transparency, increasing trust and accountability across board, fairness and bias mitigation to ensure that these models, aside the accuracy, are not biased in the predictions that are made. So my research objective in trying to validate the use of one of the uh, um, explanation method called Lime. The first thing I did was to develop and train one of such black box model on an aircraft engine data set, and also evaluate the predictive accuracy of the model. Then use Lime, which I'm going to be explaining in detail about, to explain the decision-making process of this machine learning model, then also validate the hypothesis of the instability of the method, then also implement a way of stabilizing the method. So I'll be explaining Lime as an explanation method. So LIME stands for local interpretable model agnostic explanations. And the meaning of LIME is in the acronym itself. So why is it referred to as local? So if I have a data set of several rows and predictions is being made, I I might not necessarily want to explain the predictions made across the data sets. My interest might lie in just identifying or explaining the prediction made on an instance of the data set. So Lime as a method is being designed to explain just an instance of a data set, not the whole data set across board. So say for instance, maybe in medicine, for instance, I have a data set that is comprised of different patients. Maybe different patients um, are being represented by different rows of a data set, and there's a prediction made on a diagnostic. So I might be interested on the prediction made for a particular patient. Maybe I want to explain how the model is able to predict to make diagnostic on one particular patient. Lime is a method that has been designed to do that, to explain the explanation on an instance. Then interpretable. Why is Lime referred to as interpretable? It's referred to as interpretable because inherently is being designed to interpret a much more complex model called a black box model. But then how does it do that? It does this by fitting a much more simpler model into the instance that is being predicted, and that is why it's being referred to as interpretable. Then it's being referred to as model agnostic because it can be applied to any model. It's not selective on the kind of model it can explain. Then the explanation itself is in form of feature ranking, which I'm going to show in the result of my experiment. So how does Lime really does this? How does it carry out the explanation of the prediction on an instance of the data set? So the first thing that definitely is going to be done is to select the instance I want to explain. I have a prediction that has been done on my data set across board, and I want to select an instance. So let's assume this instance to be this dot here, and now the black box model has made the prediction across for this instance. So what Lime does is it creates random points very close to that instance. That means it generates its own artificial data, but in close proximity, in close value to the point that has been selected, and that makes it a local method. So it's calculate the weights based on the distance from the chosen point to make sure that all the points are in close proximity. So the next thing it does is to make the prediction again using the black box on the new point that's been generated. Then it fits a linear model, a simpler model, across the new point that's been generated. Then it then calculates a new weight for the features in the order of importance in the order of importance for the prediction that for the new prediction that is being generated from the linear model. So is this feature rank is this weight calculation that forms the feature ranking that really explains the features that are more important in in deciding a particular prediction. But then, despite the advantage of Lime being an explainability method for explaining black box model, it has its own drawbacks as well. And one of the drawbacks that I found during my experiment is instability of the results. So I found out that if I implement Lime on a particular instance of a data set, the result I get is different when I implement it over several iterations. So I carry out multiple iterations to see if I'll get the same set of feature ranking that decides on or that influences the prediction of a particular instance of a data set. So Lime has been found out to be unstable, and this has been written in different and in different papers. The limited scope of explanation, of course, Lime as design is meant to explain just an instance of a data set, not the entire data set. So is in that way is limited, sensitive to hyperparameters, and the causes of the instability of Lime is the selection of features, the model selection, and the sampling variability. And the effect of instability of this method is reduced accountability. If I'm creating a method like Lime just to increase accountability, to increase trust among non-technical stakeholders, and the result itself is now unstable, then it's not solving the problem that is being actually designed for. And that is the essence of my research to find a way to stabilize the result of this method so that it can be trusted in use in critical sectors like the aviation sector. So in carrying out my experiment, these are the methodology. I got a sample data set, which is like an aviation data set. I pre-processed it, splitted the data set, applied a black box model, carry out Lime explanation, and validate the instability before carrying out the weight aggregation to stabilize the method or the result. So this is how the data set looks like, what I used. So we have different variables, operational settings, several sensor measurements that actually predict the remaining useful life of an engine. Um, and I splitted the data set into the training data and the test data. So the black box model of choice for me for this experiment is the graded boosting regression model, which has been found to have high accuracy. And I fitted my data set into the model and I recorded high accurate result for that. But having high accurate result is not the essence of the experiment. The essence of the experiment is to explain the prediction of the remaining useful life that is being made on the data sets. So what I did with the line method for my aircraft engine data set was to select an instance of the data set, which is one of the engine that the remaining useful life has been predicted. I selected one instance. I fitted my Lime Python, so I don't have the code here, but this is the what the result looks like. So I fitted one instance of this result of this prediction of the remaining useful life of the engine. I fitted it into the Lime result to know what variables actually contributed to the prediction of the remaining useful life of this engine. And the result of the Lime is that although definitely time is a constant factor, because as we use the engine over time, it wears off, then the remaining useful life reduces. But then there are some other factors or variables that actually speed up the reduction in the remaining useful life of an engine, which are though I didn't give detail of of what the sensor means, but let's just take it as sensor measurement numbers. So we see sensor measurement 15 being the highest contributor to the prediction of the remaining useful life of this particular engine. And for the engine I selected, this is the remaining useful life, 175 cycles. So this is the ranking results generated from this line method, and that is how it explains the black box prediction of this particular engine. But then, to validate the instability of Lime as a method for explaining um, from explaining black box model, I carry out 5 different iterations on the same instance of engine that I'm trying to explain the result. And what I discovered was the ranking actually, there's a marginal change in the ranking that was being produced. So for the first iteration that I carried out, I discovered that sensor 15, 11, 4, 13, 3 contributed to the remaining useful life. Then I say sensor measurement 14 have a positive contribution, 8 has a negative contribution. But then for the second iteration carried out, though the first 5 sensors were constant, but there's a marginal change. Sensor 12, there's raised head here, so there's a new sensor that came up in the ranking, and in the third iteration, there's a difference as well, same as well as the fourth and the fifth iteration. So if I'm going to be presenting this to the stakeholders, what I'm telling them is that this line method is not really reliable to explain the black box model. They can't rely on this feature ranking to explain the features that actually influences the black box model prediction. So what I did to solve this was the different iterations I carried out, the weights that is being used for the ranking, I averaged them out. Though before I go into that, this is a summary of the feature ranking. So these are the sensors that were constant across the 5 different iterations: sensor 15, 11, 4, 13. They had the same rank across the 5 iterations, but then these other sensors came up, which shows that this method is truly unstable because over different iterations it generates different results, which is not reliable, which doesn't facilitate trust in the black box model. So what I did was to aggregate the weight across multiple iterations such that all the features that are not really important and are coming up in the feature ranking will be averaged out. And once it is averaged out, only the ones that are consistent will show up in a new aggregated feature ranking. And when I carried out, when I wrote an algorithm for this new aggregated feature ranking, I did 2 iterations to test it out. And what I observe is it is more stable. In over these 2 iterations, I could reliably see the features that truly contribute to the prediction of this black box model. And the features are time, which is a constant already, essential measurement 15, 11, 4, 13, 3, 7, 2, 17, and 8. Same thing for the second iteration I carried out. Same set of feature ranking um, where came up in the result, and which is much more presentable to non-technical stakeholders as an explanation for how the black box model make the prediction on that particular engine that I selected. So the summary, these 2 plots represent 2 iterations of the S-line method, and it brings about the stability in the explanation of Lime as a method. And what is the significance of this experiment I carried out? And the significance is that the introduction of the weight aggregation as a technique actually boosts the acceptance of Lime as an explanation method to make black box model more trustworthy. The research also demonstrated that the S line, which is the significant improvements in Lime as a method, improves the stability of explanation over the traditional Lime when explaining complex model. By introducing this method, it improves the trustworthiness of model explanation and also adoption of this black box model in critical domain sectors like the aviation sectors and the medical sector, even sometimes even also in the finance sector as well, where transparency of black box model is really needed among non technical stakeholders to make critical decisions. And that is all for my presentation. Thank you very much.
Are there any questions? Yeah, hi, like we have a question from Sebastian.
Okay.
Well, thank you so much. I've not used Lime before, but I mean, it sounds interesting to explore it and see it from explainability parts. Um, just at the top of my head, just trying to understand. So I'm not sure if you mentioned it or maybe I missed it. How does Lime compute this the feature importance and how reliable are its ranking, most especially when it's in a high dimensional data set?
Okay. I'm trying to go back to. So this is how it works again. So after the instance of the dataset has been selected, so what Lime does is Lime generates random datasets that is close to in close value to the instance that has been selected. Then it has its own inbuilt algorithm that is used to like calculate weights of weight based on the distance of the generated data set to the instance selected. Then predicts it makes new prediction based on the new perturbed data set. Then it fits a linear model. So how it generates the feature ranking is through this linear model that has been fitted. So the linear model is trying to mimic the behavior of the black box model, but around that particular, not across the whole data set. So that's the essence of Lime itself. So if you look at the data set as a whole, it might look so complex, the prediction that's been made. But once we narrow it down to a particular instance of the data set, so Lime just tried to mimic the behavior of the black box model, which is a complex algorithm, across that local instance selected on the data set. Then it fits a linear model, and the linear model we know is easier to generate a feature ranking based on a linear model. I want to understand the features that actually contribute to the prediction than trying to like figure this out with black box model directly. So Lime just tries to use a linear model, a simpler model, more understandable model to make the Fisher ranking, and that is what is being done here in the last step, which it calculates automatically the features based on a linear model, the new feature of the weights, new weights of the features, and it uses these weights to generate the Fisher ranking.
And wow, thank you.
So
And regardless of the dimensionality of the data set, right?
but yeah, I understand when the data set becomes highly dimensional, when it sometimes it that's one I feel that's one of the drawback of Lime itself. So when
Mm,
the it
mm.
becomes a problem also when the data set become too highly dimensional, when it has too many variables as a contributor to the prediction. So I that's where I feel there's a lot of progress to be made also in explainability as a branch of machine learning.
Machine learning. Wow.
And Lime
Okay.
itself has a Python method. So all these
Okay.
has been abstracted already within a Python
Oh,
method for Lime.
okay. Okay.
Uh,
Wow. Thank you for introducing Lime to me today. I really appreciate it. Thank you.
you're welcome.
Yeah, thank you very much for a great presentation, Mr. Ogidan.
Thank you very much.
Our next